In the last video, we discussed the reduction of order. Now, we will consider two special cases of reduction of order. Now, those are two special cases. Case 1, when y does not appear explicitly, I do have missing y. The second case, when x does not appear explicitly, I do have missing x. Okay. Now, both cases can be reduced to first order easily by using the proper substitution. Now, for the first case, case number 1, y does not appear explicitly. I do have missing y from my equation. Now, in this type of equations, ODEs, I'm going to do the following substitution. I'm going to define a new variable z. I'm going to call it y prime, replace y prime with z. Then, from here, I'm going to get y double prime, which is z prime. If we make those two substitutions in my original ODE, my second order ODE will be reduced to first order, which can be solved easily by one of the techniques that we learned before. Okay, I'm going to consider a couple examples later on. Now, let's just take the second case. Case number 2, when x does not appear explicitly in the equation, I do have missing x. Now, I'm going to use the same substitution. Now, let y prime equal z. Now, right now, I'm going to take y double prime. Now, y double prime, basically, I'm going to take it as the derivative of the first derivative, which means take the first derivative, derive it in terms of x. But I have a problem right now. Since my original equation does not missing x, I will try to avoid introducing x in my equation. So I'm going to do a little kind of trick over here. I'm going to use change of variables. I'm going to write the last derivative as dy prime over dy times dy over dx. Now, this step, because x does not appear explicitly in my ODE, so I try to avoid introducing x. If I kept x over there, it's kind of I'm introducing x, so I'll try to avoid that thing. Okay, so right now, if you look to this equation over here, now dy over dx, basically this is y prime, and y prime, basically this is z. So here we go. Now, again, this is y prime, so I can replace this y prime by z. So basically, if I do have missing x, I'm going to make the substitution y prime, I'm going to replace with z. Y double prime, I will replace with z times dz over dy. And if I make this substitution, my ODE will be reduced to first order that I can solve using one of the techniques that I learned in first chapter. Now, you can see that the two substitutions are the same, but I did a little trick over here trying to avoid introducing x. Okay, let's just take one example. I will take this example, which is 2x y double prime minus 3y prime equals 0. Now, if you look to this equation, you will see that I do have x, I do have y double prime, I have y prime. This is a second order ODE. I do have missing y, so I can use the technique that I learned just the slide before by making the substitution, reducing this second order to first order. So the substitution that I will make is z equal y prime, and so z prime will equal y double prime. By making those two substitutions in the original ODE, we'll convert it to 2x z prime minus 3z equals 0. And basically, this is a first order ODE in the variable z, right? And this can be done easily using the techniques. And luckily, this one is separate. Now, by moving 3z to the other side, combining like terms, and moving z to one side and x's to the other side, and then integrate, and you will be able to get that z equals c x to the power 3/2. Now, but you know that z is equal y prime, so we will replace z with y prime. Here we go. Now again, y prime is basically dy over dx is equal c x over 3/2, Again, this is a separable ODE. I'm gonna solve, so I'm gonna get my final answer, which is y of x equal 2 halves c x power 5 halves plus a constant k. And this is gonna be the end of this ODE. Okay, so this is gonna be the solution of this given ODE. Now, just take another example. This example is y del prime minus y prime equals 0. This equation can be done in some techniques. We're going to discuss it later, but right now I'm going to use it using the reduction of order. I'll try to reduce this ODE to first order ODE. Now someone can say, oh, this is missing y, and again this missing x. I'm going to use missing x because it's a little bit more general, because those both, they are the same substitution, but the the I try to avoid introducing x in my ODE. Okay, so this is missing x. Make the substitution, y prime equals z, so y del prime will be z times dz over dy. So if you plug those two in the equation, you will be able to get, instead of y del prime dz over dy times z minus z equals 0, and basically this is first order ODE in z and y. Now move z to the other side, and of course this is separable. If you integrate, you're going to get z equal y plus c. Now again, z is equal y prime, so write y prime, and it's very clear that this is linear first order ODE. This can be found easily using the technique that we just learned, and you will be able to get that y is equal minus a plus c exponential c. And you can see this is the solution of the given original ODE. And just a quick note that if you look to the paces for this ODE, I'm going to write the first pace equal exponential x, and the second pace is equal 1 over here. Okay. Now, and by the way, as I mentioned, this can be done in an easier way. I'm gonna wait for section 2.2. Okay, this is an equation, and you can see that this is a second order ODE. This is a nonlinear ODE because I have y prime is to the third power, and I have sine of y. So this is a nonlinear ODE, and I can use the reduction of order to do such type of equations. And this is missing x. So missing x, so make the substitution that we just learned, plug instead of y prime, I'm gonna put z, y del prime, I'm gonna write dz over dy times z, and if you move those around, and you can see this is separable, and in solve this ODE, you'll be able to get 1 over z equal minus cosine y plus c. But z is equal y prime, I'm gonna write y prime, and y prime is dy over dx. Here we go. And if you make clear this fraction, we're gonna write it as dx over dy, and again this is separable. Move dy over there and integrate, and you will be able to get the final answer, which is x equal minus sin y plus c1y plus c2. And you can see that I already solved my original equation